Hello my dear students, this is Hina Kausar and welcome back to the class. Let's move on to a new concept, that is electric field, right? So to understand this, let's just recall a concept of first PU physics, that is gravitation. You have learned there about gravitational field, right? What was gravitational field? It is the region or space surrounding to a mass body where you can experience the gravitational force. For example, here you can see Earth. Earth has certain mass, right? So a mass body surrounding to that Earth, there is open space. In this region, if you bring another mass body, then what happens? That will experience a gravitational force. So this space, this region where a mass body, one more mass body can experience the gravitational force is called as gravitational field. That these things you have already learnt in your previous classes, right? Similarly, we can define electric field. How do we define it? If you consider a charged particle or a charged body, system of charges, surrounding to those charges or the system of charges, the space, you can experience the electrical force in that space. Just like gravitational field works with respect to the masses of the body, similarly, electric field can be defined with respect to the charges. Say in this example, so I have considered a plus positive charge and a negative charge, right? So surrounding to this charges, the open space or the region. In this region, if you bring one more charge, then that charge can experience an electrostatic force. Either it can be attraction or repulsion. Then this space or region we can consider it as an electric field, right? So if we have to define it, we can define it in this way. Electric field is a region or space around a charge or a system of charges within which any other charged particle can experience electrostatic forces. Either it can be attractive force or it can be a repulsive force. For example, I have considered a charge over here, right? In 3 dimension, I have considered a charge particle plus Q and I considered it as source charge. How do we define the source charge? Source charge is nothing but the charge which will produce the electric field. Okay, whichever charge we are considering is producing the electric field, that charge will be considered as source charge. So this charge is basically producing the electric field surrounding to it. So this space we can consider it as electric field. Now how do we experience that this region is an electric field? Suppose if we bring one more charge in that space, right? So let us consider this charge Q naught is the test charge. Since this charge is being used to test whether this space is electric field or not, right? Therefore it can be termed as test charge. Fine. So let's define electric field intensity. It is also termed as electric field strength. So what is electric field intensity? Electric field intensity due to any source charge at any point in its electric field is defined as the force experienced by a unit positive charge which when placed at that point. Say for example, here I have considered a plus Q charge, a source charge which is producing the electric field surrounding to it. So in this electric field, I chose this point where I am placing a unit positive charge. Now this unit positive charge obviously will experience the electrostatic force, right? Because it is in presence of electric field. It has came in contact with the electric field. So the amount of force which is experienced by this unit positive charge is called as electric field strength or electric field intensity at that particular point. Okay. Mathematically, it can be expressed as vector E is equals to vector F divided by Q naught. That is, electric field intensity is equals to force per unit positive charge, right? Suppose if you consider this test charge very infinitely small charge, right? In that case, you can rewrite this expression as vector E is equals to limit of delta Q tends to 0 vector F over delta Q. Whenever we are considering delta Q as vanishingly small quantity, then we will apply the limits as delta tends to 0. Or just by substituting the value of vector F from Coulomb's law, we can rewrite this expression for electric field as electric field vector E is equals to 1 over 4 pi epsilon naught Q divided by R square into R cap, where the Q naught term will get cancelled both in numerator and denominator. This Q naught and the Q naught which will present in the force expression will get cancelled, and the remaining term we will get it as this. Fine. So further few more important points you should remember relating to electric field. Let us just have a look at it. So very first thing is, in this example, if you are considering a unit positive charge which is placed nearby to a source charge which is also positive, then what happens? Obviously you will observe electrostatic force of repulsion. So force direction will be away from the source charge, right? And in this case, electric field direction will also be acting along the force direction, that will be away from the source charge. But in case if the source charge which you have placed is a negative charge, and in the electric field which is produced by this negative charge, you are placing a unit positive test charge at one particular point, then obviously we will observe a force of attraction, electrostatic force of attraction, and that force of attraction will be, direction will be towards the negative source charge, right? And in this case, the electric field direction will also be along with the force direction, that is towards the source charge. Okay. Now you might have understood, it's clear that electric field is also a vector quantity. Just like force is a vector quantity, it has both magnitude and as well as direction. At any point, at every point in the field, we can define electric field, its magnitude and direction uniquely, right? And how we can measure it? The SI unit of electric field is Newton per Coulomb. Why? Because it is force per unit charge. Force is expressed in terms of Newton and charge is expressed in terms of Coulomb. So SI unit of electric field become Newton per Coulomb. And dimensional formula for this electric field, we can derive it as capital M, capital L, T to the power of -2, A to the power of -1. This you have learnt how to derive the dimensional formula in first PU physics So we will not be going in deep here. One more important term is uniform electric field. Now when do we say electric field as an uniform electric field? Say suppose in the electric field at many different points will be there, right? At any point, if the strength of the electric field and if the direction of the electric field is same, if it is remaining same at every point, then such kind of space or such field we call it as uniform electric field. Say suppose for example in the electric field, if the strength and the direction of the electric field is different at different points, then such type of field we call it as non-uniform electric field. Okay, these terms we might be using in future in the chapter. So remember these important terms. Let's derive an expression for the electric field due to a point charge. I am just considering a simple example. Due to a point charge, what will be the amount of electric field generated? For that, let us consider a three-dimensional space which is having three dimensions, that is x coordinate, y coordinate and z coordinate. I'll be considering a point charge which is being placed at the origin. Now at point P, which will be having coordinates x, y, z, I have placed a unit positive test charge Q naught. Now since it has came under the influence of this electric field, this unit positive charge will experience a electrical force which will be away from the source charge, because Both the charges are of same type. Therefore, we will observe electrostatic repulsion. So, force direction will be away from the source charge. And let us consider the distance between the source charge and the test charge is given by the position vector r. Okay, so this is our consideration. Now, the force which is extended or exerted due to this source charge upon this test charge can be given by simply the Coulomb's law, that is vector F is equals to 1 over 4 pi epsilon naught Q into Q naught divided by R square into R cap, where Q is the magnitude of the source charge, Q naught is the magnitude of this test charge, R is the distance between the source charge and the test charge, and R cap, it is just the unit vector which will give the direction of this force F, right? Or you can also express it as, if you are not expressing it in terms of direction, the vector in terms of direction, then you can consider the magnitude and rewrite the expression as vector F is equals to 1 by 4 pi epsilon naught Q naught divided by R cube into vector R. Now, what will be the electric field strength? Electric field intensity. We know electric field strength or electric field intensity is defined as force per unit positive charge, right? That is given by vector E is equals to vector F divided by Q naught. Now, in this expression, if we substitute the value of vector F, which we have already defined here according to Coulomb's law, right? So, on substituting, we get vector E is equals to 1 over 4 pi epsilon naught Q divided by R cube into vector R. Why? Because this Q naught will get cancelled with the denominator Q naught, right? So, those two terms will get cancelled. So, remaining terms will be remaining in the expression. Or you can rewrite it as, in terms of unit vector, if you express vector E, and that is the electric field at the point R, will be equal to 1 over 4 pi epsilon naught Q divided by R square into R cap, where Q will be the magnitude of the charge, R will be the distance between the source charge and the test charge, and R cap is the unit vector which will give the direction of this electric field. Now, if you observe this expression, on what factor does this electric field depends? This electric field is directly depending upon the magnitude of the charge which you are placing. If the magnitude of the charge is more, then the electric field strength will also be more. That is the source charge I am talking. Okay. And what about the distance? As you can see, it is inversely depending. If the distance increases, then obviously the electric field strength will go on decreasing. In this graph, you can see that variation as the distance has been squared, and as it goes on increasing, the electric field strength will go on decreasing, because both the quantities are inversely depending. Which means now I guess you are clear why we are considering only certain distances when it comes to practical situations, because as the distance goes on increasing, the magnitude of the electric field strength, it will obviously go on decreasing, because of which we will not consider infinite distances and consider only certain countable distances. So, one more important point what you should remember is the electric field due to a point charge will have a spherical symmetry. How? Say for example, here you have considered a positive charge, right? Which means Q will be greater than 0. Then the electric field will be acting radially outward, because the direction of the field will be along the direction of the electrostatic force, and force is always acting outwards, right? Similarly, if the charge is a negative charge, that is if the Q value is less than 0, then the field will be radially acting inward, because there will be force of attraction between this test charge and the source charge. So, if we are considering only the magnitude of the electric field intensity at that point P, then the equation can be given by E is equals to 1 over 4 pi epsilon naught Q divided by R square. Since we have considered only the magnitude, we are not using any vector notation here. We haven't used the arrow mark over the letter and neither we use the unit vector to represent the direction. Then what about the direction of the electric field? It will be represented by the direction of the position vector. In whichever the direction the position vector may lie, the same direction will be given to the electric field. In terms of coordinates, if we express the electric field, then we can express it as vector E will be equal to 1 over 4 pi epsilon naught q divided by, instead of that position vector r, we can replace it by the coordinates as x square plus y square plus z square whole to the power of 3 by 2 into xi cap plus yj cap plus zk cap. So this is how we can express electric field in terms of coordinates. Now let's just have a quick review of the derivation. So electric field due to a point charge, how do we derive it? We will consider a source charge at origin O, and we will place a unit positive charge, a test charge at point P, which is at a distance r from this source charge. Then this test charge will experience a force vector F, which is given by the Coulomb's law, that is vector F is equals to 1 over 4 pi epsilon naught q into q naught divided by r square into r cap. This q is the magnitude of the source charge, q naught is the magnitude of the test charge, and r is the distance between source charge and the test charge. If we rewrite this expression in terms of, if we replace this unit vector and write it in terms of both magnitude and direction, then we can express the equation as vector F is equals to 1 over 4 pi epsilon naught q into q naught divided by r cube into vector r. Now according to the definition of electric field intensity, we know that vector E can be expressed as vector F divided by q naught, that is electric field intensity or field strength is force per unit positive charge. So just substituting the value of vector F from the above equation, we will get the expression for electric field strength or electric field, that as vector E is equals to 1 over 4 pi epsilon naught q divided by r cube into vector r. How we got this? Just by eliminating this q naught charge, because it gets cancelled from numerator and denominator. So remaining part is this only the source charge magnitude. Right? So final expression is vector E is equals to 1 over 4 pi epsilon naught q divided by r square into r cap. By observing this equation, you can see that electric field will vary according to the distance. As the distance goes on increasing from the source charge, the magnitude of the electric field will also go on decreasing. If the distance between the test charge and the source charge go on decreasing, then the magnitude of electric field strength or the electric field intensity will go on increasing. So this is how we will derive electric field, which is produced due to a. Let's move on to the next concept, that is electric field intensity at a point due to a system of charges. Just now we had derived expression due to a single point charge, but now we are assuming that there are many number of charges or system of charges. Now how we can find the electric field intensity? It is not possible just by using the Coulomb's law, right? So now what we will do, we will make use of the principle of superposition. What is principle of superposition? In the previous session we had used it in case of electrical forces. What was according to that? It was according to that we determined the electrical force due to multiple charges. It was just the vector sum of the forces which is exerted due to multiple charges at one particular point, right? So the same principle of superposition now can be applied on the electric field as well, right? According to principle of superposition, the electric field at any point due to the group of charges is equal to the vector sum of the electric fields produced by the individual charges at that point when all other charges are assumed to be absent. Okay, this is the principle of how to make use of the principle of superposition to determine electric field intensity. Let's have a look at it. For that, I'll be considering there is a system of charges. System of charges Q1, Q2, Q3, so on up to Qn, which are distributed in space in discrete manner, in random manner. Okay. Now in this group of charges, I'll choose a point P where we are going to determine the electric field strength or electric field intensity. Okay, and I'll place a test charge at this point P, that is Q naught. Okay, now this Q naught will experience the force, electrostatic force, which is exerted due to the different charges, right? And hence we will calculate the electric field intensity which will be experienced by this test charge Q naught at point P. So the group of charges Q1, Q2, Q3, Q1 exert forces, those are F1 plus F2 plus F3 so on up to Fn on the test charge which we had placed at the point P here, right? Now let us consider a charge Qi, which is that is the ith charge which is being placed here. Okay, I am considering this charge. The force due to this charge will be given by vector Fi, right? If we write it in terms of Coulomb's law, the force due to ith charge exerted due to the ith charge will be equal to 1 by 4 pi epsilon naught Qi into Q naught divided by Ri square into unit vector Ri cap, where Qi will be the magnitude of the charge Qi, Q naught will be the magnitude of the test charge which we have placed at this point P. Okay, so this Qi charge is exerting force on this point P, on this test charge Q naught on point P, that is given by vector Fi, and mathematically I have written it here in this way, right? Where Ri is the distance between this ith charge and the test charge, right? And Ri cap will be the unit vector which will give the direction of this force which is exerted due to ith charge on the test charge. Therefore, the electric field which will be due to this ith charge on this test charge will be given by Ei. Vector Ei is equals to limit of vector Fi divided by Q naught, because the test charge which we have considered is very small. Okay, so in this expression, if I just substitute the value of vector Fi from the above equation, we get this equation. Vector Ei is equals to limit of Q tends to 0 into 1 over Q naught into 1 over 4 pi epsilon naught Qi Q naught divided by Ri square into Ri cap, which is this Q naught. It is the denominator Q naught. I have placed it here separately, right? And the remaining terms are the substitution of this Fi vector I have made here. On simplifying it further, this Q naught and numerator Q naught will get cancelled. So remaining term will be vector Ei is equals to 1 over 4 pi epsilon naught Qi divided by Ri square into Ri cap. So what will be the direction of this electric field? The direction of this electric field will be along the direction of the force on this charge Q naught. In whichever the direction the force is exerted due to ith charge on the test charge, in the same direction the electric field will also be acting. Now similarly, this is just one charge I have considered, right? So you just have a look at here. I have just considered this ith charge. In the same manner, the same way, the force and the electric field will be exerting on this test charge due to all other charges, right? So what we can consider, we can assume that vector E1, vector E2, vector E3, so on up to vector En, all the electric fields due to the charges Q1, Q2, Q3, so on up to Qn on the test charge Q0. So if E is the electric field at point P due to all the system of charges, if I consider vector E is the total electric field intensity or the total electric field on the point P, at the point P on the test charge Q0, then according to the principle of superposition, what it states? It states the total electric field will be the vector sum of all the electric fields which are contributed due to the system of charges. Therefore, vector E can be written as vector E1 plus vector E2 plus vector E3 plus so on up to vector En, or this summation can be expressed as summation of I is equals to 0 to n. I we can take values of 0, 1, 2, 3, so on up to n vector ei. So on substituting the value of ei cap in this equation, the final term, that is the electric field due to the system of charges, can be given by vector E is equals to summation of I is equals to 0 to n 1 over 4 pi epsilon naught qi divided by ri square into ri cap, where I will take the values of 0 to n, q will be the magnitude of the charge, and r cap will be the unit vector which will give the direction of this electric field. So this is how we will derive the electric field intensity or electric field strength due to system of charges. If there are many number of, let's have a quick review on our derivation. So we were supposed to derive an expression for electric field intensity at a point due to a system of charges. For that we made use of principle of superposition. We considered n point charges, that is q1, q2, q3, so on up to qn, which are distributed in space, and we considered a point P. At this point P, we placed a unit positive charge, a very small test charge q naught. At this point P, what will be the electric field intensity due to these many system of charges? That we are going to derive. So we are going to derive expression for this electric field intensity at this particular point P. For that, what we did, first we considered that all the charges q1 to qn will be exerting forces f1 plus f2 plus so on up to fn on the point P, right? In those many number of charges, we chose particularly one charge called as qi, ith charge we considered, and the force due to that ith charge can be given by Coulomb's law, right? So that expression I have written here, right? After that, the electric field due to that ith charge is calculated. How? Just by substituting in this definition, that is vector ei is equals to limit of q tends to 0, that is fi vector divided by q naught. If you just substitute the value of fi vector here, you will get the final expression of ei vector, that is electric field due to ith charge on the test charge. So now since you have got the electric field due to ith charge, in the same manner, according to superposition principle, the system of charges will be applying individual electric field on that test charge, right? So therefore, total electric field will be given by electric field vector electric field E is equals to vector E1 plus vector E2 plus vector E3 plus so on up to vector En. These are the electric fields due to the system of charges Q1, Q2, so on up to Qn. If you replace it by simple term, it can be expressed as summation of I is equals to 0 to n vector Ei. So substituting the value of vector Ei, which we have already determined over here, you will get a final expression for the electric field intensity due to system of charges. So electric field intensity due to a linear charge distribution. In one of the sessions we had discussed regarding linear charge distribution, right? We had also derived an expression for force due to this linear charge distribution on a unit positive test charge, right? So that expression is given by vector F is equals to 1 over 4 pi epsilon naught q naught into line integral of lambda dl divided by r square into r cap, where lambda is the linear charge density. Now using this, we can also write an expression for electric field intensity due to this linear charge distribution. By the definition of electric field intensity, we know vector E can be expressed as limit of q tends to 0 vector F divided by q naught. By the definition of electric field intensity, we can express vector E as limit of vector F divided by q naught as q tends to 0. Now by substituting the value of vector F from the above equation, we can write the vector E as 1 over 4 pi epsilon naught line integral of lambda dl divided by r square into r cap. When we substitute the value of vector F here, this q naught in the numerator will get cancelled by this denominator Q naught. So remaining term is the expression for electric field intensity due to a linear charge distribution. Similarly, we can also calculate the electric field intensity due to a surface charge distribution. We had derived the expression for force due to surface charge distribution, right? So what was the expression? Vector F is equals to surface area integral of 1 over 4 pi epsilon naught Q naught into sigma ds divided by r square into r cap. And according to the definition of electric field intensity, we know that vector E is equals to limit of vector F divided by Q naught, right? As Q tends to 0. Substituting the value of vector F from the above equation, we get the expression as vector E is equals to 1 over 4 pi epsilon naught surface integral of sigma into ds divided by r square into r cap. Again here you can observe this numerator Q naught will get cancelled with the denominator Q naught as you substitute the value of vector F. So this is the expression we are going to use whenever we want to write the expression for electric field intensity due to surface charge distribution. Similarly, electric field intensity due to a volume charge distribution. To write the expression for electric field intensity, first we will consider the force expression which is due to volume charge distribution. The expression is vector F is equals to volume integral of 1 over 4 pi epsilon naught Q naught into rho into dV divided by r square into r cap. Now according to the definition of electric field intensity, we know the definition of electric field intensity, vector E is equals to limit of vector F over Q naught as Q tends to 0. Substituting the value of vector F here from the above equation, we get the final expression for electric field intensity due to a volume charge distribution, that is 1 over 4 pi epsilon naught integral of rho into dV divided by r square into r cap. Right? So as you see here, this numerator Q naught can be cancelled with this denominator Q naught and the remaining term comes in the final expression. So this is the electric field intensity due to different continuous charge distributions. So far in this class we discussed about electric field. What is an electric field? Electric field is a region or space around a charge or a system of charges within which other charged particles will experience the electrostatic force, right? We discussed few important points relating to this, that is electric field intensity. What is electric field intensity? It is the force experienced by unit positive charge when it is placed at that particular point. And also we came across whether electric field is a scalar or vector. It's a vector quantity. Electric field intensity can be expressed in terms of Newton per Coulomb, right? We discussed about uniform electric field and non-uniform electric field, and also we derived an expression for electric field due to a point charge which is given by vector E is equals to 1 over 4 pi epsilon naught Q divided by r square. And electric field varies with distance. As the distance increases, electric field will decrease. And also we derived expression for electric field intensity due to system of charges, right? So according to the superposition principle, we made use of it and derived expression for electric field intensity due to system of charges, and that expression is vector E is equals to summation of I is equals to 0 to n 1 over 4 pi epsilon naught Qi divided by Ri square into Ri cap, where I will take values from 0 to n. And also we discussed about electric field intensity due to different continuous charge distribution. Due to linear charge distribution, it will take the value of vector E is equals to 1 over 4 pi epsilon naught line integral of lambda into dl divided by r square into r cap. Similarly, electric field intensity due to surface charge distribution is vector E is equals to 1 over 4 pi epsilon naught surface integral of sigma into ds over r square into r cap. And electric field intensity due to a volume charge distribution is vector E is equals to 1 over 4 pi epsilon naught volume integral of rho into dV divided by r square into r cap. So these are all the expressions which you should remember, which will help in future when we are trying to solve some practical numericals. I hope you liked this video. We will continue in the next session. Till then, take care.